Now that we can talk about the domains of these functions, what is really useful, or why do we really want power series, is because we have seen that when they converge, for example, that's the domain, um, then certain functions can be represented as power series, which is really neat because not all functions are polynomials. Or well, it's power series is not a polynomial, but it behaves like one or can be approximated by one. This means that I can derive some formulas just from this. If I know that 1 over 1 minus x is 1 plus x squared, so on, what happens if I replace x by negative x squared? Then I get 1 minus negative x squared, or 1 over 1 plus x squared is 1 minus x squared plus negative x squared squared plus negative x squared cubed, and so on, which is 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus x to the 10, so on. So if I have one of my functions, then I can define the other one. And then I don't have to worry too much because if x is less than 1, then x squared is definitely less than 1. What happens if I replace x by negative x? Then I get 1 over 1 plus x is 1 minus x plus x squared minus x cubed plus x to the 4 minus x to the 5, so on. Now you can also do operations. What if I take the derivative, right? So the derivative of 1 over 1 minus x must equal the derivative of its power series. What's this derivative? That's 1 over 1 minus x whole squared. And this is 0. This is 1 plus 2x plus 3x squared plus 4x cubed, and so on. So what is happening here is that when you take the derivative, this is a series where you have increasing powers of x and you have the coefficients which are also increasing by 1. And that equals 1 over 1 minus x whole squared. You could also take the integral. That's a valid operation. This is going to be ln of 1 minus x. Let's take the integral of 1 plus x, and that's going to be integral of, this was 1 minus plus minus. So if I take the integral, that's x minus x squared over 2 plus x cubed over 3 minus x4 over 4, so on. So I get a nice approximation of even a logarithmic function using just x's, as x minus x squared over 2 plus x cubed over 3. So here the denominators are increasing as well. Find a power series representation for 1 over x plus 2. What you can remember is 1 over 1 plus x, is 1 minus x plus x squared minus x cubed, so on. So you can think of this as 1 over 1 plus x plus 1, which means this would be 1 minus 1 plus x, 1 plus x squared, 1 plus x cubed, so on. So these are little tricks that you can, it's more like finding a pattern and solving the problem and being able to see what to use and being really creative about how to find the power series representation. Find a power series representation of this term now. Now, we already have one for 1 over x plus 2. And this is nothing but x cubed multiplied by this, which means that for the power series, I could just multiply x cubed with a power series representation of 1 over x plus 2. So now this is x cubed minus x cubed x plus 1, x cubed x plus 1 squared, and so on, with an alternate plus and minus. So The reason we can do this is because there's a theorem which says that if a power series is differentiable on the interval, the radius of convergence of the power series, its derivative, and its integral are the same. So basically, tells you that you are allowed to do all those operations. Express 1 over 1 minus x squared as a power series. What is the radius of convergence? So let's go back to 1 over 1 minus x. This is 1 plus x squared and so on. If you take the derivative, we've seen that you get that, and the derivative gives me a new power series where the coefficients increase by 1. And by definition, my radius of convergence is the same as this. Right? So the radius, even for this, is 1, and the interval is the same, which is -1 to 1. Okay, let's look at another example. Find a power series representation for tan inverse x. Now we have to really sort of be very, very creative about this. So the motivation is, how do I get tan inverse x from this expression? So we have to really dig deep here and remember that this integral is tan inverse x. So we first need to find this 1 over 1 plus x squared. So I replace x by negative x squared, and I get 1 plus x squared, which becomes 1 minus x squared plus x4 minus x6 plus x8 minus x10, so on. We've seen this before. And then if I integrate this, I know on my left hand side I'm going to have tan inverse x minus x cubed over 3 plus x to the 5 over 5, x to the 7 over 7, x to the 9 over 9, and so on. So I get all the odd powers divided by the coefficients. That's the power series representation for tan inverse x. So once again, there is no fixed rule. You have to be very cognizant of all the things that you've learned, so that you can use them to find the power series representation of the function that you are interested in. That's it for this week.